Hi, I'm Carl Wimmer, and I'm going to be talking about testing data bindings. This is joint work with Clement Canon from IBM Almaden. So let's get into the testing part. We're going to be working in the standard distribution testing model. We say that an algorithm tests a property P of distributions, which is just a set of distributions, if given access to samples from an unknown distribution little p. If little p has the property, it's in the set capital P, then the algorithm accepts. If little p is epsilon far from the property P, then the algorithm rejects. And we're using, for farness, the notion of total variation distance, which is a number between 0 and 1, given by the formula on the screen. And so if the total variation distance is at least epsilon for all q in the property capital P, then the algorithm rejects with probability 2/3. And the goal here is to minimize the sample complexity of such an algorithm. This is the standard model for distribution testing. So let's see what a data binding would be. So we define a data binding to be this, which is something we have not seen in the literature. Formally, P is a binding of Q if there exists a non-decreasing total function f such that the ith element of Q probability is the sum of the bunch of consecutive probabilities of P. And the way that f is set up here, that these things all have to be in order. Q is a distribution over little k, or brackets little k rather, the elements 1 through k. And P is a distribution over brackets capital N, the integers 1 through capital N. Capital N will often be much larger than little k. And so let's look at an example here. So is little p a binding of Q here? And it turns out that the answer is indeed yes, and so we can color code things to see that. So here the first three elements of P have a total probability mass of 0.5, matching the first element of Q. The next four elements of little p have a total probability that matches the second element's probability mass in Q, and the last elements of each distribution match here. And this is an instance where k is 3 and capital N is 8, even though only 7 of those elements have a non-zero probability mass. This is a little bit easier to see if we use a pie chart for these things instead, because then once we put everything together and color it, then the pie charts are exactly the same except for the transition points in P. So if we go back to the definition then and look at our example we just did, the non-decreasing function f sort of tells us essentially how to color these graphs. And again, this function f is non-decreasing. And also instead, we don't have to use a function f like this. We could instead use an interval partition. We could break up brackets capital N into k intervals such that then that the ith element of Q has a probability mass that's the sum of the probability masses of elements in the ith interval. And of course, there's not too much difference here. I prefer the f version here that we had, so we'll go back to that. But our question here then is going to be, how can we determine if P is a binding of Q with few samples? And so here we have complete access to Q, but only sample access to this unknown P. And we're trying to determine if P is a binding of Q, again, trying to use as few samples as possible. So this is a new problem that has pretty much no information on it in the literature as far as we could tell. So we give the first upper and lower bounds for this problem. So upper bound, k over epsilon squared samples suffice, which is completely independent of capital N. And the lower bound is close. It's essentially k over epsilon. It's not quite all the way there. There's a small factor of k in the denominator as well. So we're going to spend the rest of our time here talking about these two bounds. The upper bound will take quite a bit less time than the lower bound, and so we'll start with that one. So to get a little bit handle on what it would mean to be far from binding here, we'll define this binding distance to be essentially what is the smallest possible absolute error we could see if we try to do some sort of binding. And if P really is a binding of Q, then the binding distance is going to be 0. And if P is epsilon far from every binding of Q, well, then that means that the binding distance is at least epsilon over 2. So this binding distance is standing in nicely for the total variation distance, except that it's not really a nice thing to work with in some sense. So for example, it's not symmetric in its arguments. So we'd like to use something that's a little bit nicer. And luckily enough, there is something for us, something known as the a sub k distance. So if we have two distributions over a common domain, then the a sub k distance is the maximum total variation distance between a common binding of P and Q into at most k bins. And so what we mean is that if we take an interval partition of brackets N into k pieces, and we add up the probabilities inside each of the interval pieces, and we compare then how what is the absolute error in the corresponding intervals for these total probabilities that we've added up? Well, what is the maximum that we could be off? And so here, these probability mass functions evaluated at an interval is just what you would expect, the sum of the individual probability masses inside that interval. This is an interpolation of the CDF distance or Kolmogorov distance between two distributions. That would be the case when k is 2, and when k is n, then we recover the total variation distance. Okay, so what can we do with the a sub k distance? Well, by VC dimension arguments, and these have been used in a few property testing papers in recent years, we can learn an unknown distribution up to a sub k distance epsilon with k over epsilon squared samples. And so this is better than testing because we actually get a hypothesis distribution, which with high probability is going to be close to the unknown distribution in a sub k distance. Now the definition of a sub k distance looks very similar to this binning distance that we were talking about, because we're talking about the total absolute error when we break things up into k pieces. And so one thing we prove, up to some small things here that aren't quite right, it depends on how you treat the elements with probability 0, is that for every reference distribution we could be looking at, and then every pair of distributions over capital N, the binning distance to Q for both of these distributions can't be really that much different as long as they're the same, or as long as they're close, rather, in a sub k distance. So if we can learn a distribution up in a sub k distance, well, we could use that for the binning distance. So our algorithm then is to just learn a distribution p prime such that it's close to the unknown distribution in a sub k distance. And then now we have p prime, we have q, we have everything we need. Then we just look to see what the binning distance is. This step doesn't require any samples, and it could be very computationally expensive to do this because there could be lots of ways to sort of chop up these elements, but we can find the best binning efficiently with a dynamic program, and so the running time then is polynomial in capital N. And that's pretty much the entire upper bound. So that takes care of that, and we will spend the rest of our time then talking about the lower bound. So for the lower bound, what we're going to do is we're going to talk about a restricted version of the data binning problem that we're going to call identity up to binning. So we have the same problem, same definition rather, up as before, but we're going to make a further assumption that the support sizes of P and Q are exactly K. Now P here is still a distribution over capital N, where capital N is still much larger than K, but we're going to assume that there are only K elements that have non-zero probability mass. So then for this to really be a binning, what we can think about then is that there's an increasing function f, because each of these bins rather would have at most one element in it. And so then we're really just looking for this nice sort of bijection between the supports of P and Q. Now in the reject case, we're going to reject things that are far from any binning, not just those that happen to be in this form. Of course, it turns out without too much work then, through the uniformity testing lower bound, we can sort of massage this to get a lower bound of root k over epsilon squared using the Binnings' lower bound for uniformity testing to also apply here. This takes not too much massaging to see this. So we get at least this. Of course, this isn't going to be k over epsilon squared, and our resulting bound is going to have worse dependence on epsilon. So what kind of algorithms do we need to consider? So one sort of thing we can notice is that if n is really much larger than k, then the exact names in the support of P don't actually seem all that helpful. I mean, if there are only a few elements, say, 100 or so elements in the support, and we see these 4 samples here, and we see something twice, which suggests that it might have larger probability mass than many of the other elements, for example. Well, we don't know what the names of the other elements are. So there could be many elements in the support that are between 5552368 and 8675309. Maybe there are none. And so these names don't really help us a whole lot, and all we can really get out of this is that we saw 2 elements once, and something between them we saw twice. And so to formalize this, we're going to call this a fingerprint. And so a fingerprint of m samples is a vector such that the ith thing in this list is the ith thing in order, and we saw it f sub I times. And so, for example, for the sample that we have above here, these 4 samples, the fingerprint that we see then is 1, 2, 1. And so that might really be, if n is really large, the only actual information that we get. And so the theorem that we prove is we exactly formalize this, that if we have an M-query tester for data binning, where capital N is large enough, then there's also an M-query tester for this identity up to binning problem. And the tester is only allowed to look at fingerprints. It doesn't have to look at anything else. And so while P is going to really be on some K elements, or sorry, supported on some K elements out of brackets N, if the tester is only going to look at fingerprints, it might as well be a distribution over brackets K as well, but that's promised that it's only allowed to look at fingerprints and nothing else. Now, how do we prove this? We're not going to have time in this talk to actually go through the proof of this, but it uses a Ramsey theory-like argument. Specifically, it uses a theorem of Conlon, Fox, and Sudakov that was also used in at least one property testing paper in Diak-Nicholas et al. And the idea is that we can, essentially, for any tester that we have, if we look at its behavior on subsets of brackets capital N, we can find K elements where its behavior only looks at the fingerprints, no matter what type of tester we have. And so formalizing that takes a bit of work. The argument is a little bit different than the one in, say, Diak-Nicholas et al. That's cited here, but we were able to make it go through. So then we can assume that the algorithm is only allowed to look at fingerprints, and we'll use this to construct a hard instance of identity up to binning. Like many other papers in property testing, or in distribution testing, where these distributions will have some sort of block structure to them, where there are blocks of some certain size B, and our distribution then is going to be uniform over the blocks, and then conditioned on a block, we'll have to put some structure in there. So as a first step to get something, let's try a block size of 2, and we'll try distributions that have an element of probability 1/3 and probability 2/3. And so we have these two distributions, which are going to be far apart in total variation distance, and let's see if these are hard to distinguish. If we're looking at just one single block, then if we look at the fingerprint only, then these things are indistinguishable from two samples. The probability that you would see something twice is going to be 5/9. The probability that you see two different elements would be 4/9 from two samples inside that block. So if you see at most two things in a block, that's not really going to help you distinguish anything. Now the fingerprint for the whole set of samples is just the concatenation of the fingerprints for each block. Just take all of these vectors where there's something that is actually seen, and we'll just chunk them all together. That's the fingerprint for the whole block. So if each block looks exactly the same, and the fingerprint for the entire set of samples is just a concatenation of these things that look the same, then the fingerprints for the entire set of samples really looks the same. So you get no information for distinguishing, again, under this thing that we are conditioning on, that you see at most two samples in each block. If you see more than two samples in each block, then all bets are off, and this, of course, does not necessarily work. So that sounds really good, except that we said that they were far apart in total variation distance, but oops, they're not exactly far apart, they really aren't far apart in the binning distance that we care about. So if we try to line these things up, and we look what happens, well, we might be off on the first part here, so this bucket might be empty, and this part on the end is going to be a problem, but everything else in the middle can line up perfectly. So these distributions are actually very close to each other, but they're just kind of offset. And so if you're only going to see fingerprints, then yeah, these distributions are going to be hard to tell apart, because if you don't see the first blue element or the last orange one, then they really are the same. But in terms of binning distance also sort of knows this and says these distributions are very close to each other. And so this isn't really fair in some sense, because our epsilon parameter would have to be very, very small. So this doesn't really give us a helpful lower bound, because we would like this distance, this epsilon parameter, to be constant. So we're going to have to fix this a little bit, and there's not too much to do here. So here's a different probability distribution over set of probability distributions rather, over 3 elements each. And these are indistinguishable from two samples. And we've picked the order on these particularly so that it's not possible for these things to be close in binning distance. Now that would take a little bit of effort to actually go through, because we'd have to say no matter how we try to bunch things and sort of pinch things together and skip things, that we would get, it's impossible to get two things that are close to each other. That really happens. I'm not going to say any more about it than that. So If we're looking at just fingerprints, as long as you receive at most 2 samples from any of these k/3 blocks that we make, then our fingerprints are not going to help. Again, in each block, we have the same distribution over fingerprints. If we concatenate, then we're going to get the concatenation of what happens over each block, so we'll get things that we can't distinguish. So as long as we satisfy this condition, then we're good. Is it likely that we'll satisfy this condition? Well, yes, from full caloric collision estimates, we want to make sure that we get at most 2 samples in a block. This is going to be very likely as long as we have, say, fewer than k to the 2/3 over k to the 2/3 many samples. At this point, this is where it becomes kind of likely by birthday paradox type arguments that we would see 3 samples in at least one of these blocks, and at that point, we're just going to give up. And again, this bound holds for some constant epsilon that we're not going to try to work out here. So how would we improve this? So we'd like to get a pair of blocks that do the same kind of thing. Maybe the blocks will have to be longer. We don't want to have this 1/3, 2/3 business that we saw, so we don't want to see these kind of shifts of each other. And from fingerprints, we want to make sure that at most m samples don't help in any one block. Our conclusion then is that we'll have k/b blocks. By collision estimates, then we'll have to get k/b to the m/m+1 many samples in order to distinguish these two things. So then let's see what we can do here. The way that we're going to set this up is that we're going to set up distribution so that half of the elements, we'll assume that b is even, have mass slightly less than 1/b and slightly more than 1/b. Picking these specifically so that binning doesn't really help, that there isn't anything you can do by pinching things together. And let's consider any possible fingerprint that we could possibly see. And we want to work towards what's the probability that we would actually see that fingerprint. We're trying to show that these distributions would be the same. So there are at most 2 times b to the m ways to realize this fingerprint from m samples by just doing some sort of stars and bars argument. And what kind of things then would we see in this probability? Well, it would be the sum of all of the ways that we could actually realize this fingerprint. And so we would get at most 2b to the m terms that are a bunch of products of 4/5b's and 6/5b's. And so how many could we get? Well, it's okay. So the 5b over m's we can factor out. If we see the samples in a different order, but we see the exact same samples, then because samples are drawn IID, then we are going to have the same probability for that. So we can factor that out. And that leaves some integer s in the front. And how large can this integer be? Well, there are at most 2 times b to the m things that we're adding up. The only thing we haven't accounted for are these numerators. And so we might be adding up things like 6 to the m over 5b to the m. And so s is going to be at most 12b to the m. Now for each, how many fingerprints are there that we have to deal with? Well, these are positive integers that add up to m. And so there are at most 2 to the m ways to do this, where the order matters. So there are at most 12b times m to the 2m possibilities for the distributions of all of these fingerprints. And so let's keep this up on the screen here. And just by counting, just looking at a binomial coefficient and approximating it, there's about 2 to the b total such distributions that we could possibly be looking at. And so we'd like to apply the pigeonhole principle to find 2 that have the same distribution over fingerprints. And so we'll take b to be something like m squared times 2 to the m and apply the pigeonhole principle. And now we have 2 distributions that match as long as we have fingerprints that go up to m samples. So if we see at most m samples in each block, then we can't distinguish these things. Of course, we talked about this at the beginning of our goal, but we didn't actually put it in anywhere, because what if we get something like this, like we saw before, that do match, but they aren't really far apart from each other? So we do have to handle this case. So we're going to disallow what we'll call partial cyclic shifts. So not exact cyclic shifts, that one is just the other sort of shifted around cyclically. We also want to insist that no large subsequence of one distribution occurs as a subsequence in another, possibly with one wraparound. We're not going to wrap around more than once, but this will handle the case that then when we sort of stitch these blocks together, that we aren't going to see the same sort of mapping repeated from one to the other. So if we say, look at these 2 things here as a bad example, if we look at the orange distribution, the first 7 elements appear as elements 3 through 9 in the blue distribution. And elements 8 and 9 of the orange distribution are then the 11th and 12th elements in the blue distribution, so skipping one in the blue. Then wrapping around on the blue, the first and second elements of the blue distribution are the 10th and 11th elements of the orange distribution. And so these are things that are kind of bad here because we see that blue is pretty close to a cyclic shift of the orange one. And we prove with a bunch of work that this is really the only bad thing that could happen, that everything will go nice for us as long as we can show that there's no large subsequence like this here, that these guys aren't partial cyclic shifts of each other. Now, of course, for us to have a large subsequence just by counting, it turns out that for every distribution that this form, there aren't really that many that are partial cyclic shifts. And so we show that there's, at least compared to 2 to the b, there aren't that many distributions that are going to be, for our parameters, partial cyclic shifts of it. Which leaves us with about 2 to the 4b over 5 such distributions, such that no two are partial cyclic shifts of each other. And then now we can copy what we did before. So we'll take b again to be something like m squared times 2 to the m and apply the pigeonhole principle. And now we've covered all of our bases because now these distributions really are, with some work that we did not show here, are going to be constant far and binning distance once we look at all of these things when we put the blocks together. And we'll have matching distributions over fingerprints, again, as long as we have up to m samples that lie in any single block. So if we go back to our goal conclusion slide from before, then we really do get our lower bound here that we said, as long as we take b to be about m squared times 2 to the m. And then if we want to balance these parameters to make this lower bound as large as possible, we'll choose m to be the square root of log k for a lower bound that's pretty close to k, of course up to exponential in something like root log k. And again, this is for constant epsilon, and we wanted to get something for all epsilon, but with a standard trick of just making one element that has a very large probability mass, and then just epsilon mass on this construction that we made, we can get a lower bound that also has epsilon in it. And so that gives us the lower bound that we came up with. And again, it's not on the slide here, but I'll remind that we also have a root k over epsilon squared bound that follows from Binnings' lower bound for uniformity testing. So then we introduced this data binning problem, and we gave upper and lower bounds on it. But of course, there are many open questions still. So one of them is the tighter dependence on the parameters here. So k we don't get quite right. Epsilon we get pretty close. We get quadratic versus linear. And this capital N, maybe we don't need to be quite so large. I mean, we had to use a Ramsey theory type argument multiple times, which means that N has to be extremely large. It still only depends on k, but still could be extremely large. Maybe N only has to be polynomial in k to achieve this lower bound. We can also ask the question of what happens if both p and q are unknown rather than just p, where we have to make samples to q as well. Ask for samples from q in order to determine if p is a binning of q. And finally, one more general question that's less structured is what happens in other domains. So if we aren't talking about distributions over the line, but if we have something over grids or hypercubes or something like this, and we want to talk about what it means to be a binning of something else and testing that, what does that even mean? And can we do it? All right, thank you for watching.